Oh, I don't think that was it.
Thank you. Sorry.
You just erase it all in their hand? Yeah. And then wipe it on your head. Or you just write it over.
Okay. Okay, so we have... So we have length contraction, and we have time dilation, right? So the proper distance is decreasing, and the proper time is increasing. Looks like it's dilated. And we have the last formula I want to show you is like velocity when we add two reference frames. So we have v1 plus v2 divided by 1 plus v1 v2. I took c equals 1. And obviously if one of them will be c, everything will turn out to be c. The other one will be c as well. Sorry, 1. So there's not too much here that I want to show you. If you went through, I think what concerned me is to show you how we use relativistic physics and particle physics. So I think that will be, I'm sure you did tons of exercises from what I heard last time, so I don't need to do it. Okay, so let's see how do we deal with particle physics and how we include relativistic physics in particle physics.
Why do we have to?
Why we have to is because these things decay at speeds that have to consider.
They move very fast. Fast things, special relativity.
That's
Big
right.
things, general relativity.
Yeah, well.
All things, quantum mechanics.
Okay, well, you have quantum mechanics, you have field theory, you have like...
Oh, that's what quantum field theory.
Quantum field theory is just...
Quantum mechanics
and
with relativity.
that's right. That's
I
right.
read the beginning of Griffiths.
Good. That's right. That's the first thing he says. That's right. Okay, so first, what I wanted to emphasize, because we cannot do anything without knowing how do we mathematically write these things, what are the symbols and what is the math behind it. So for 4 vector, what you know, so we're going to work always with 4 vectors. Now x0 will be t, x1 will be x, x2 will be y, it's the only time that I will ever write it, and x3 will be z. So this is my 4 vector. Now, no, I did 3, 4. I jumped 1 page. No, I'm good. Okay. Okay, so first, the way I write Lorentz transformation. So this vector will be written as the notification will be x mu, where mu goes from 0 to 3. Oopsie. Now, Lorentz transformation will be written as this matrix So I will write it once, but after that it will always be assumed. So this is the Lorentz transformation. So this is mu and nu. This is because each one of them is going from 0 to 3. 0 to 3. Right? It's the column. And so you will have to do like, this is contravariant, this is covariant, contravariant vector. This is just names of vector. This is Einstein's summation that I will show you.
So contravariant means it's the column?
Yeah, I mean, I never remember the name, but you will have to, it really doesn't matter. It's just like you have to be consistent, like in physics, always be consistent. Like columns and row, and if like, as long as you're consistent, then you're fine. So we also had anything, anything that transform like x mu, like this one, is called a contravariant. And, right, contravariant for vector. Now,
when it's up, it's contravariant?
Yeah.
When it's small, below? Okay, up.
I think up it's contra, the other one is covariant, is the, yeah.
So I'm just trying to figure this out. Are the mu and the nu supposed to be, so the mu, if the mu is the contravariant one, then shouldn't it also be...
This is a metric, so this is different.
So
a matrix is basically a multiplication of a contravariant and a covariant. You can think about it as if you multiply a vector like this by a vector like this, you get a matrix. So basically it's a tensor.
Yeah, it's the Lorentz tensor, right?
Right. So another thing I need to introduce you is something that we call Minkowski matrix. So Minkowski matrix is Minkowski matrix, yeah. Minkowski somewhere.
Yeah,
right. Minkowski metric.
Oh, okay. This is sort of general relativity.
No, well, it's used.
It's used in general relativity at least.
It's a simple thing in general because it's a flat matrix. The simplest, right? It's the simplest thing. So the Minkowski matrix is, how do you say, Minkowski, whatever. It's like -1, -1, -1. This is the idea. The rest are 0.
Is that the method tensor for this space?
For what we're talking about, yes. We will assume only Minkowski.
Does it matter if you have those 3 negative ones, or if you make the first one negative and the rest positive?
Be consistent. Be consistent. You can do what you want as long as you're consistent.
Well, what do most physicists do?
We do that.
So this is the more common one.
This is the common one, but if you do it the other way, you know, it's like potential, how do you say, energy, right. So this is like, pick your reference. Anything in physics is like that. Just be consistent. And now, if I use this metric, obviously you remember from the proper time that delta S, I think you wrote it, would be delta x0 squared minus delta x1 squared minus delta x2 squared minus x3 squared. So I think you remember that.
Is that the delta S squared?
Sorry?
Is that delta S squared? Or
It's ds. I think we write...
Squared, right?
I don't know. It's like the world potential. It's a world path. So we can call it square too. So yes, it is. You're right. So in the new notation, it will be written as nu delta x mu delta x nu. So
That's Einstein's notation, right?
it's all Einstein notation, yeah. It's using the metrics and Einstein summation.
Would both use the up on the delta x's? Would they both have up mu's because of the same quantity squared?
In this one, yes.
And would that be a nu or a...
It's mu nu.
Oh.
Right.
Wait, but
That's the Einstein convention.
then
That's it.
Then you would have, then you can have delta x0 times delta x1. So I don't
No. You have to take all the different values. It's a summation.
Yeah,
so
yeah.
0, 0, 1.
Oh, yeah, never mind. I see. Yeah, but
Right.
those coefficients would be 0.
Right. That's right. So, and you also know that x mu, to turn a covariant into from contravariant to covariant, you just have to multiply by the Minkowski matrix. So this is how we move from contravariant to covariant. Now, to prove that the matrix, Minkowski matrix, is Lorentz invariant, we can do a small, just show it very quickly.